So we started two-dimensional kinematics. This is of a particle. So we're still not dealing with rotations or objects with length dimensions. And we defined mass, and I said that we're going to think of mass as just a resistance to accelerations. And then I gave the most important equation for this whole class, Newton's second law. I'm going to always abbreviate that N2L, Newton's second law. And Newton's second law says if you add up all the force vectors acting on an object, so we're going to call that F net, that's equal to the mass of the object times the acceleration of the object. So this F net is the sum of all forces acting on the chosen object. And M is the mass of the chosen object. And A is the acceleration of the chosen object's center of mass. And we started to define forces. We started to talk about forces. I did say that forces in this class are going to be broken up. Well, I think maybe you could say just generally. It doesn't have to do with this class or other classes. Forces can be broken up into two categories. The first one is the weight force, the force applied by gravity. Really, that's the weight force is a subset of force fields. And so gravitational force is a force field. There are some other types of force fields like electric fields, magnetic fields. We're not going to talk about any other ones except gravity. But if you think of those as one category, then that's the first type of force we'll deal with. And the second one, and these two categories account for every force that we're going to deal with, are contact forces with other objects. From touching objects. And I think this is a really useful way to think about it because we're going to get into complicated problems where it can often get a little, like you first glance at the problem and you're asked for like what kind of force is being applied to the thing by this. And there's a lot of things going on and it can be sort of complicated to intuitively you look at it and you're like, how am I going to know when I've accounted for all the forces? How am I? Well, if you think of it this way, it's easy to know when you're done accounting for the forces. You're going to account for the weight force that gravity applies to things, and then you're going to go around the boundary of your chosen object. Like say your chosen object is the wheel of a car. You're just going to go around the boundary and look at any place that outside objects are touching the boundary. And at each one of those contact places, there's a force. And once you've accounted for all those contact forces, you're done. Okay, so it's a nice sort of uh, centering technique, like it's a nice way to break the problem down into just a um, sort of a systematic approach to getting through all the um, going through all the forces. Okay, so let's start um, talking about the different kinds of forces, how you know what kind of force vectors are applied. Um, so first, let's deal with the weight force. And weight is the force applied by gravity. Um, and we're going to be able to figure out what the weight force is applied to an object by analyzing an object that's in free fall. So to figure out the weight force on an object, let's consider an object with a mass of m, lowercase m, in free fall. Okay, so um, here's our object with a mass of m. And what do we know about something that's in free fall? Yeah, so if it's in free fall, we know that the acceleration vector is 0 for x, negative 9.81 meters per second squared for y. That's if we have our y-axis pointing up. Um, and so think about the definition of free fall. What forces are acting on an object that's in free fall? Gravity, and that's it. That's the definition of free fall. Um, and we also know that the only force acting is the weight. Okay, so based on that, let's fill in Newton's second law. Um, so Newton's second law says add up all the force vectors acting on the object, and that's just a force vector of, well, so I'm going to write that as the force of the weight. I'm going to break it up into x and y components. That's what we're going to calculate. And that's equal to the mass of the object. We said we're dealing with a mass m, so mass times the acceleration of 0, negative 9.81. And now we can break this up into two separate equations. The x and y equations, what's happening in the x component doesn't have any effect on what happens in the y component and vice versa. So I'll break this up into an x component equation that says F sub W x component is equal to 0 times m. So that's 0. And the y equation says F sub W y component is equal to negative 9.81 m. And a lot of times you'll see that written as negative mg, where that g is 9.81 meters per second squared. Okay, so what this tells us is gravity applies a force magnitude of mg down to an object with mass m. And we use free fall conditions to calculate this. But this is true whether the thing's in free fall or not. So this is a force applied to an object no matter what else is happening to the object. Okay, so I want to take a minute to talk about this in relation to the common misconception number one that I talked about. So how does this relate to common misconception number one? Okay, so what is common misconception number one? That's right. So I think the wording I used was something like uh, gravity makes a larger mass accelerate faster. And it turned out that no, gravity doesn't do that. When that does happen, it's just because air resistance slows down the less massive thing more than the more massive thing. So if there's no air resistance, um, objects accelerate down at an acceleration of g, 9.81 meters per second squared, regardless of the mass. But look at what this result just said. We just calculated the force that gravity applies to things. So now we see that the force gravity applies to objects is proportional to the mass. Okay, so the question is, how can both of those two things be true? You know, um, this is a super confusing thing. Um, so if you go into that vacuum chamber and drop a bowling ball and a feather, and they both accelerate down at 9.81 meters per second squared. Now we calculate the force that's applied to those, and the bowling ball has a much bigger force applied to it than gravity does. So how can these two things both be happening? Yep. That's exactly right. Yep. So, like, the way this works is since mass is resistance to acceleration, okay, if you had a bowling ball and a feather and you wanted them both to accelerate 9.81 meters per second squared, you'd have to apply a bigger force to the bowling ball. It has more resistance to acceleration. Okay, you need to apply a bigger force to overcome that. And so that's the relationship between these things. Gravity, so it seems like sort of a paradox or something at first when you, if you're, before you've thought about it this way. But both of these two things are true. Gravity does apply a bigger force to things with more mass, but gravity doesn't make things with bigger mass accelerate more. Um, so let's see. How can that be? Um, and the answer is mass is resistance to acceleration. So to make two objects accelerate down at 9.81 meters per second squared, gravity has to apply a bigger force to a more massive object. All right, so now we already have one thing we figured out. That's great. Now let's figure out, uh, here's an example problem. Let's say that there's a scale sitting on the floor and a man standing on the scale. And let's say the man has a mass of 100 kilograms. And we want to know what's the force vector applied to the man by the scale. Um, okay, well, Newton's second law says that we're going to add up all the forces acting on the man. Um, so that's what we're calling the net force. And that's going to be equal to the mass of the man times the acceleration vector of the man. So this is the sum of all the force vectors. On the man. So the man is going to be our chosen object. The mass of the man is the mass of the chosen object. And this acceleration vector is the acceleration vector of the man, the chosen object. And let's use a coordinate system like this. Okay, so what forces are acting on the man? Well, gravity is always acting on anything. Um, and now we know that the force of gravity, so let's break it up. The force applied by gravity, the weight, is equal to 0 in the x direction. It's always a downward force, so then negative 9.81 times 100, so 981. And the units are newtons. We're doing everything in SI units. So this negative 981 comes from negative 9.81 times 100. And to figure out any other forces acting on the man, we have to think of, so the only contact force is the force applied to the man by the scale. Any questions about that? And then do we know anything about the acceleration? Well, we're imagining that he's just standing there, so he's not moving at all. Then there's no velocity, and if the velocity never changes, there's no acceleration. So the acceleration vector is 0x, 0y. And now we can put this all into Newton's second law. So the sum of the force vectors is 0, negative 981. The force vector applied by the scale, we don't know what that is, so I'm just going to call that F scale, break it up into an X component and a Y component. We have to calculate both of those. And those are equal to the mass of the man, 100 kilograms. So on the right side is the mass times the acceleration, and then the acceleration vector of 0, 0. And now we can break this equation up into an X component and a Y component. The X equation says 0 plus F scale X is equal to 100 times 0, so 0. And so F scale X is equal to 0. And then the Y component equation says negative 981 plus F scale Y is equal to 100 times 0. And so F scale Y component is positive 981 newtons. So to put this all together into a force vector, the force F scale vector has a 0x component and a y component of positive 981 newtons. And then, in other words, if this is the coordinate system, plot that point. So go 0x positive 981y. You get a vector that looks like this, magnitude of 981. So another way to say this is a magnitude of 981 newtons. Okay. So the force is applying, scale is applying a force of 981 newtons up on the man's foot. Feet. Okay, so that's how a bathroom scale works, you know. So you're not really trying to, like, you don't really care how much force the bathroom scale is applying to your foot. You really want to know is how much force gravity is applying to you because that's proportional to your mass. And the way you use a bathroom scale to calculate, you know, you have this thing that measures the amount of force it applies to your feet. And you get on it where the only two forces acting on you are uh, the scale and gravity, and then they have to be equal and opposite. They have to be the same magnitude in opposite directions. Okay, so say you want to lose weight. So what can you do to lose weight without diet or exercise or, you know, without waiting a whole bunch of weeks and stuff like that? That's a pain. There's no C in exercise, I don't think. Exercise. Okay. So we're going to do the same thing again. So same question, but this time the scale and the man are on an elevator that's accelerating down at, let's say, 2 meters per second squared. Um, accelerating down at 2 meters per second squared. Okay, so here's the elevator. It's accelerating down at 2 meters per second squared. And on the elevator is a scale. And here's the man. You probably shouldn't ride an elevator in your underwear like this, but okay, so what's the force applied to the man by the scale? All right, well, we're going to use Newton's second law. So F net vector is equal to the mass of the man times the acceleration of the man. F net is the sum of all the force vectors on the man. M is the mass of the man. A is the acceleration of the man. Okay, so let's figure out what we know about this stuff. For the sum of the forces, first there's the force applied by gravity, the weight force. And do we know what that is? Yep, so the fact that he's on an elevator doesn't have any effect on that. Gravity just always does the same thing. So that's going to be equal to 0, negative 981. And the units for force are newtons. The mass is 100 kilograms. And what do we know about the acceleration of the man? That's right. So he's just riding the elevator. So whatever the acceleration is of the elevator, that's the acceleration of the man. So this is equal to 0, negative 2 meters per second squared. So Newton's second law says, well, what forces are acting? The gravitational force is acting, 0, negative 981. And now we have to think about all the contact forces. Where is the outside world in contact with the chosen object? Just the scale. Nothing's changed about that. So we still just have F scale X and F scale Y. And that's equal to 100 times the acceleration, 0, negative 2. So the X equation says F scale X is equal to 0. I guess to expand on this, the X equation says 0 plus F scale X is equal to 0. So F scale X is equal to 0. And the Y equation says negative 981 plus F scale Y is equal to negative 200. And solve for F scale Y, and you get positive 781 newtons. So if you write this as a force vector, the force applied to the man by the scale is 0, 781 in newtons. Or another way to think of that is 781 newtons up. Okay, so I want to lose 200 newtons of weight according to the scale. Get on an elevator accelerating down at 2 meters per second squared, and the scale will read this lower value. That's the same thing, like you kind of know that this effect happens because you can kind of feel it in your stomach when the elevator starts to accelerate down. Then when it gets up to a constant speed for the rest of the trip down, you don't feel anything. At that point, the acceleration's 0. So this would only happen right at the start of that motion. And what do you think happens if you're on the scale and it's accelerating up at 2 meters per second squared? Yeah, the scale would read it would read 981, right, plus 200. So, yeah, if you're ever, you're like trying to fit into your dress for the prom or whatever, propose that they do, if they did the whole prom accelerating down at 2 meters per second squared, well, your dress still wouldn't fit. That's true. Um, yes. For F net. That's right. Yep, that's right. The weight is still the same. The weight is the force that gravity applies, and that never changes. What changes is just what the scale reads.